What's up, good people? This is section 6.4, graphing radical functions. This is your boy, Mr. Bergman, coming to you from my basement. All right, so we got what we really want to do here is we want to graph these radicals for the first time ever. We're going to see some parent. These are new parent functions. You can see the square root of x, and I just want to remind you that anytime we are anytime we're graphing things, or anytime we're using functions, that we're not going to be using imaginary numbers, because what are we going to do if we get an answer of negative 3i? Where are we going to put that here? We just can't. There's no space for imaginary numbers on the real plane. So we're just going to ignore the fact that we really could take the square root of negative 4 and get 2i. But we're not going to. We're only looking for real numbers here. So if you put negative 4 into this function, you can't get anything. You can't get any real number out. Negative 1 doesn't happen either. The action really picks up when you start at 0. So you can take the square root of 0, you get 0. You can take the square root of 1, you get 1. I'm going to choose not to go like 0, 1, 2 here, because it'll just make it be a lot easier if we choose perfect squares as inputs. The square root of 4 is 2, square root of 9 is 3. And you can plot them. This is the point 9, 3 right here, the bottom row. 4, 2 gets plotted right here. 1, 1, 0, 0. Great. Let's take a look at cube roots. Again, I'm going to only choose perfect cubes over here because I don't really want to plot any decimals. So if you choose perfect roots over here, then that means you can take the other cube roots and then you get the answers over here. So 20, what's the cube root of 27? Well, that's like what number times itself 3 times is 27? That's 3. What number times itself 3 times is 8? That's 2. The cube root of 1 is 1. The cube root of 0 is 0. The cube root of negative 1. What number times itself 3 times is negative 1? That's negative 1. What number times itself 3 times is negative 8? That's negative 2. You actually can take cube roots. Whenever this radical, whenever the type of radical is an odd number, you can actually work with negatives here, and that's fine. So you can see it actually extends. This is the point negative 8, negative 2, the top row. This is the point negative 1, negative 1, 0, 0, 1, 1, and 8, 2, right here. It gets plotted, and the curve looks like this. It's kind of an S shape. It is a function. It passes the vertical line test. All vertical lines only touch the point. Even here along the y-axis, there's only one point, even though it gets super steep. And it does pass the horizontal line test as well, as we'll see. Let's actually talk about the properties of each of these functions. I'm going to move myself up here. And so this is what, here's what the functions look like. So let's talk about the parent function square root of x and the cube root of x. The transformed versions of that would be, you can put h on the inside, k on the outside, and the transformed version would be a, like the vertical dilation a would be over here. What is the domain of this function? The domain of the square root function would start at 0. The lowest x value is 0. There's no highest x value, so it goes from 0 up to positive infinity. The range is the same thing. Y is the lowest y value is 0, and it just keeps on going up. So it goes from 0 to positive infinity. The cube root is going to be different. There's no lowest x value, there's no highest x value, so the domain is from negative infinity to infinity. The range, the lowest y value, again, there's none. There's no highest y value, so the range spans all real numbers from negative infinity to positive infinity. Yes, both functions pass both the vertical lines test and the horizontal line test. You can draw horizontal lines and vertical lines all day and only pass through one point. The vertex, this right here is 0, 0, unless of course it gets transformed, like it might get transformed to h, k, and that might be a new vertex. Here, we're actually not going to call this a vertex. We're going to call it a point of inflection, but same idea. It starts at 0, 0, and it can get transformed depending on what h and k end up being. At the moment, the x-intercept is 0, but that would change if you moved it around. And at the moment, the x and y-intercept for both of these is 0. And of course, it changes if you transform it, move it up, down, left, or right. End behavior. This stopped. It only leaves this function only leaves the graph once to the right here. It only leaves the window once to the right here. So you can say as x goes to infinity, as x gets larger and larger and larger, then y will also get larger and larger and larger. You can go as high as you want in the y values just by simply going as high as you need to on the x values. And so that's end behavior. You can kind of say that the cube root function has down, up, end behavior. It leaves the window here going down. It leaves the window here going up. Where is it increasing? It's increasing along the interval 0, infinity, where it's defined. And this is always increasing here. It's never decreasing. It never flattens out completely. There's no symmetry on this one, unless, of course, you're going to somehow draw the lower arm of the parabola. Then it would have reflectional symmetry. But we're just looking at this as a function. And here, there's rotational symmetry about the point of inflection right here. Let's see what happens when we start introducing some transformations. So, let's say we had the graph y equals square root of x plus 7. Well, looking at that here, we actually don't even need to look at the graph. I know there's going to be a horizontal shift of -7. I see x plus 7, and I just flip it around because it expects subtraction. So this would be a horizontal shift of -7. There's no vertical shift because there's no number on the outside of the square root. This -7 is inside for horizontal. So that means the new vertex, the old vertex would be at 0, 0. But the new vertex would be shifted over 7. It would be at -7, 0. This is the location on the graph. There's no vertical dilation, no horizontal dilation. And so the new domain would be -7, infinity. The lowest x value you could have here is 0, but because of this shift, you have a new lowest x value would be -7. The vertex shifts over -7, and so you could say the domain here is -7, infinity. The range is unaffected because it's just a horizontal shift. Moving right along, let's take something a little bit more complicated. Here you can see there's 3 different numbers. There's a 5, a +2, and a -1. The +2 is on the inside, so that's going to be horizontal. It's going to be a horizontal shift of -2. The whole thing is going to be moved over to the left 2 units. The vertical is going to be a vertical shift because I can see it's -1 on the outside. So that means the new vertex, the old vertex used to be at 0, 0, but now because of these 2 shifts, you got a new vertex at -2, 1. This is the location on the graph. Plus, on top of that, it's going to be vertically dilated. It's going to be stretched. It's going to be 5 times as steep as it normally would be. All the y values get multiplied by 5. So, what does that mean? That means that the new domain, because of the horizontal shift, you have a new lowest x value. It's -2. It used to be 0, but because of the horizontal shift, the domain is -2, infinity. And the range, you have a new lowest y value because you can subtract -1 right here. The vertex is now down to -1, so the range is from -1 to infinity. Let's go to cube root land. All right, so we've got 3 numbers here. We've got a horizontal shift, a vertical shift, and a vertical dilation. You can see x -2, so we see a -2 and switch that around to get +2, 5 is where the new point of inflection is. Used to be at 0, 0, as you can see here, but the new point of inflection, everything got shifted to 2 units to the right and 5 units up. There is a vertical dilation of 4. You can see that's the number out in front here. And there's no horizontal dilation yet. The domain is going to be unaffected. Actually, it's a lot easier than before. And the range is unaffected because, it went down as far as you wanted in both the x and y directions and went up as far as you wanted in both the x and y directions. So it's still going to be -infinity to positive infinity for both. Cube root. All right, check this out. Cube root of 7 times the cube root of x -3 over 5 plus 2. There's 4 different numbers. The -3 turns into a horizontal shift of +3. The +2 on the outside is a vertical shift. That means that the new point of inflection is at 3, 2. It used to be at 0, 0, and now it got shifted horizontally and vertically. The new it also has a vertical dilation, 7. It's going to be 7 times as steep. And the horizontal dilation is 5, because I got that from the number that's being divided right here, 5. Domain and range are unaffected. All right, before we move in to this next page, I wanted to drop an audio check and just say that my favorite thing to do, let me tell you what my favorite thing to do at Chipotle is. Maybe I start off with a base as choose the tortilla or something like that, but very quickly I move in and say, hey, you know what, Chipotle worker who is helping me out right now, I just want to say you're probably much better at coming up with really tasty Chipotle combos, much better than I am. I'm terrible about that. I always get way too much in the wrong things. Why don't you make me your favorite thing? So I asked the server to make me their favorite Chipotle burrito or bowl or whatever it is, and and it's just really cool to often just see them be experts in their field, and they come up with some really tasty stuff that I love. Of course, anything from Chipotle is going to be tasty because that's how they roll. That's your audio check. Um, I wanted to talk about parent tables. So these parent tables, for the first time, really, it's going to be way, 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 way slam dunk easier to do a parent table than do a strict graphing table. And that's because of how complex the square root function is. If you just let's think of some numbers that you can easily take the square root of. You can easily take the square root of 0, 1, 4, and 9. Now, if you just straight up do a graphing table, 0, 1, 4, 9, and you let, it's going to be tricky because you're going to get decimals, and graphing the square roots of decimals is really complicated, and you might also get numbers that are off the allowed alex.com grid. So I'm going to say that you really got to use the parent tables this time. That's okay, because the parent function of the square root, we can take these numbers that are easily square rootable. The square root of all these numbers is right here, 0, 1, 2, 3. So how do we turn this into, if you were going to simply graph the f of x is equal to square root of x, we're done. These are the x values, and these would be the x values, and these would be the y values. But we've got some transformations going on. Outside of the square root, we can see there's a vertical dilation of 2, so I'm going to do that first. I'm going to take all these y values and I'm going to double them because it's times 2. You doubled all these numbers, vertical dilation times 2. You doubled all these numbers, you get not 0, 1, 2, 3, but 0, 2, 4, 6. It's going to make the overall graph steeper. All the y values got doubled, so it stretches it out like that. But then there's also going to be this plus 1 afterwards in that order, so we also then have to take all these numbers and add 1 to it. It's going to shift all the, it used to be at 0, 2, 4, 6, and now it's going to shift it up to the y values of 1, 3, 5, and 7. So, and it's incredibly important that you make sure you do it in that order also, like in PEMDAS order. But here, thinking about the x values, we've got, as we can see, a horizontal shift of -3. And so I have to subtract 3 from all of these numbers over here. I'm going to do it to this side. So the horizontal shift of -3, take all these numbers and subtract 3, and you get these numbers here. These are going to be your x values, and all the way over here are going to be your y values. If you plot -3, 1, it's here, and -2, 3, it's up here, and +1, +5, it's over here, and 6, 7, it's over here. 6, 7. I wanted to say that this would be really tricky to do if it were just a input-output table, graphing table, because you would have to come up with these numbers, -3, -2, 1, and 6 as your start, because when you put -3 in here, you get -3 plus 3 gives you 0. Then you take the square root, and you get 0, and then you multiply by 2, and you get 0, and you add 1. But coming up with these x values is incredibly tricky to start off with. Way easier to use a parent table. You start off with the parent, and then you transform it from there. I want to say that what I just did, starting with -3 and running it through to 1, is actually a great way to proofread to make sure you got the numbers, especially if you're in like a testing situation. You could take all 4 of these and just run it through and make sure. Let's start with 6. If we actually input 6, what do we output? We put 6 here, and you add 3 to get 9. Then you take the square root of 9, and you get 3. You multiply by 3 by 2 to get 6. I'm just doing PEMDAS. And then 2 plus 1 gives you, 2 times 3 is 6, and then 6 plus 1 is 7. So this x value and this y value are what we plot, and we confirm it because we actually subbed in 6, and if 6 is the input, then 7 is the output. Let's do the same thing down here. Again, parent table. Again, cube root function, super complicated, and it's going to be way easier to use a parent table. So let's think of some numbers that you can easily take the cube root of. And you can see they are these numbers here. Yeah, you can take the cube root of 8 and 1. You can also take the cube root of 0. You can even take the cube root of negative numbers. And when you get to ALEKS, you're going to see that the instructions are going to require that you have what might be called the vertex or the point of inflection right here, the center of symmetry, and then two numbers on either side. So, so what are the cube root of these numbers? They are these here. 2 times itself 3 times is 8. So when you ask yourself what number times itself 3 times is 8, it's 2. And they have their negative corresponding numbers over here. All right, so let's start talking about transformations. On the outside, the vertical ones are easier to think about because you can see this times negative 3. So I'm going to multiply all these y values by negative 3. And you get this. This negative 2 times negative 3 is 6. Then there's the vertical dilation is times negative 3. The vertical shift is going to be minus 2. So I subtract 2 from all these numbers, and I get 4, 1, negative 2, negative 5, negative 8. You can see it's steeper, it's flipped from what you might expect from the parent, and it's also shifted down 2 units. The horizontal one's always tricky to think about. I see x minus 1, so therefore it's a horizontal shift of plus 1, which is the opposite. And I'm going to add 1 to all of these numbers here. These were the old x values, but I have to shift them over 1 unit. These are the new x values. Move my head. Okay, so take all these numbers and add 1, and you get these new numbers. If you plot these negative 7, this is the x value, and all the way over here is the y value. Negative 7, 4, all the way up to 9, negative 8. You plot them, you'll get numbers that are reasonably fitting on a zoomed-in graph, and you'll get enough of them that they actually work. And there's no decimals and no fractions and no cube roots to worry about. You can double check. Let's take 9. If 9 is the input, what's the output? So put 9 in here. 9 minus 1 is 8. Cube root of 8 is 2. Then 2 times negative 3 is negative 6. And negative 6 minus 2 is negative 8. You run it through. The input is 9. The output is negative 8. So we did it correctly. It's a great way to check. Is that all? Is that all? Is there no one else? There's nobody else. All right. Thanks for listening. Thanks for watching. I'll see you in class. And why don't you tell me what your favorite Chipotle is?